Welcome, everyone, to my talk about dependencies and Kotlin Native, or versus Kotlin Native, because sometimes they don't really go well together. Before I tell you something about myself, let's take a look at the agenda. We will look at the differences and similarities of dependency management, compilation, and the whole compilation process, and linking, and then execution between JVM and the native. And then we'll take a look at some common problems and possible solutions / workarounds for them. So a little bit about me. I began programming in PHP, then I've done some C#, and then Java for Android and for backends. So I was living in that virtual machine bytecode world, fully unaware what native is. I was self-taught, so I didn't have any computer science background that would show me all of those nasty things in the native world. But then I wanted to do iOS, and iOS is all native, unless you want to use something that's like React Native, but I didn't want to, so I went to Objective-C and then struggled. And now with Kotlin Multiplatform being in the picture, a lot of Android developers have the same problems that I saw, either because they did computer science a long time ago and they don't remember, or they didn't pay attention. So I want to help with that. I want to show you how it's different from the JVM world. And for simplification of all of this, I'm not gonna be looking into like how Android works because one, it changed over time, and two, it's more complicated than just pure JVM. And then on native, because Kotlin Multiplatform is mostly for mobile, so Android and iOS, we'll just be looking at the Darwin platform, which is the Apple's watchOS, macOS, iOS, and tvOS. So let's dive into the comparison, starting with JVM. In JVM world, we have plenty of dependency management tools from Ant, Ivy, Maven to Gradle. And we just declare the dependencies that we want, and then they get resolved. Right now, we don't really care where they get resolved from. We just care that they get resolved into jar files. And again, for Android, it's slightly different. But for all intents and purposes, it's just classes that are pre-compiled into bytecode in jar files. Now, we don't care about the package names or anything, so I will make it simpler, and we'll have just a jar and b jar. Now, those jar files come pre-compiled and are executable. They may not have everything to be executed, but if you include them in your program, you can call any code in them and it will just work. So we start with those jar files. We extract, the compile process extracts them and extracts the classes, the class files. And then your Kotlin code, when it's compiled, it can use public declarations from those class files and the additional metadata that's included to compile against them and then use them from your code. And then that foo class gets compiled into foo. That's the bytecode file, and in turn gets bundled into a jar file. Usually we have a lot of those class files in a single jar file. For simplicity, we just have foo. And then when it's time to execute, we create class path, which is essentially just either those jar files or the .class files themselves that we provide to the virtual machine and tell it, these are your classes, please work with them. And since the jar files are just zip files, we can merge them into a single one and then give it to the JVM, and it will work as if we gave it every single jar file like in the slide before. This is what we call universal jar, and this will be important later when comparing to native. Now, we've run our JVM, everything works, and it should run everywhere, as the marketing says. How about native? It's not as simple. We do have dependency management, but it's working a little different. So at this point, for iOS at least, you can use one of these three. You can use CocoaPods, you can use Carthage, Swift Package Manager. Essentially, CocoaPods and Carthage are deprecated in a way. However, if you really wanted to use them, you could. But your iOS folks will probably be wanting to use Swift Package Manager. So no matter what we use to declare those dependencies, whether it's CocoaPods, Carthage, or Swift Package Manager, we get something. And we don't know what that something is. And it's usually the dependencies decision whether it's gonna be a precompiled or so-called rendered framework or a source package that you then compile on your machine. The vendor framework can be either static or dynamic, and we'll get to that later. But what's important here is all of these will contain some kind of interface. In our case here, it's header files. For simplicity, we're gonna be talking about C because it is not having a lot of these high-level niceties like overloading and async stuff and whatever. It's just as low as we can get while still writing source code to the native machine code, essentially. So what the compilation does then is it takes a single source file, so your .c file, and headers that the source file is referencing. And the headers can reference other headers. They can never reference another C file, another source file. And then the compiler produces a single object file. So for each source file, we run the compilation. We can run them in parallel, so that's nice for us. And then we get a bunch of object files. Now, these object files are machine code. And you have to decide what architecture you build for when you're building them. And they will be architecture dependent. So if you're building for your iOS, it's gonna be ARM64. If you're building for your old Mac, that's Intel, it's gonna be x86-64. And they won't be interchangeable. However, even though it's machine code, we cannot run them. We just compile them, but there's no way we could just say, please, my PC, I want this to be running now. And that's because it has undefined symbol references, usually. Like you could get a very simple program that doesn't have them, but because these are essentially non-existent, you need another step, which we'll get to in a bit. So to show it in a visual way, we now have the dependencies A and B for our code that we got from a dependency manager, whether it's CocoaPods, Carthage, or Swift Package Manager. And as I mentioned, they contain the header files. So we essentially extract those header files, and then this is the compile. Now, from the point of view of the compiler, our header file, the foo.h, is as any of the other header files. It doesn't care. So I could have just put it next to each the rest. But I want to highlight, like, this is our compile unit, right? And the foo.c is our source code. That's where the implementation lives. And we get a foo.o, an object file. Object file contains symbols. So I want to pause here and tell you what symbols are. They are quite simple, but I still had trouble like understanding them. So I want to compare them to Java again. So in Java, we have two-level symbol table. So we, at the top level, have classes. And classes are represented by their fully qualified domain name, which is the package name. In this example, it's com.example. And the class name, which is A1. And then every class have their own internal declarations. So here we have hello world, that's a function or method. And then we can have A2, which is a field. Notice that the hello world signature, and the signatures here, or like the symbol names, are bold, contains the parentheses. And that allows Java to overload methods by the parameter types. So we can have hello world with no parameters, and we can declare hello world, the same name of the method, with a single Boolean parameter, for example. Now, in C, or in the native world, things are simpler, but also a little more complex. We only have a single level, and those are textual symbol names. Everything exists on the global level. So those are all symbols. Now, in C, if we declare a function hello world, like this, only the hello world itself is the symbol name. We won't be able to declare another hello world with no parameters. We would have to name it differently, with an underscore or 0 in the name. So that's how you get all those str CPI, strn CPI, and all of these weird overloads that need to change the name. And then global variables are also symbols. So we could not have a function hello world and at the same time a global variable hello world, because they would clash and we would not compile that. Symbols are also used for metadata for high-level languages. So for example, Objective-C uses this Objective-C underscore class underscore $sign underscore and then the name of a class to declare symbols for Objective-C classes. And then at runtime, it can ask the dynamic loader, please give me all of the symbols that are declared and start with this prefix. And that's how it registers all of the Objective-C classes for its dynamicity, where C itself is very much static. This is how Objective-C can have that dynamic behavior. And I would say lastly, but there's so many other uses of symbols. The last that we kind of like want to know about is debug information. When you compile your C code, it doesn't need to know about the structure of the memory. So it can basically forget. If you're then building a release, if you were using this structure, foo, in memory, it's just the integer. That's all it is. So once we strip the debug symbols, we no longer know what the memory layout and structure was looking like. But now, I didn't really tell you what symbols are, just what they are used for. And I struggled with the idea of symbols, and perhaps I'm the only one here that struggled with it because it's so simple that it kind of was like, oh, there has to be more to it. It can't be just simple. Nothing is simple in software, is it? Well, it kind of is. So your symbol table is essentially just this. It's like you have a name of the symbol, so A1, and the address where in the binary it is. And then when you load that during execution, the dynamic loader will move it around in the memory and put it somewhere, so it will update this address. But in the end, that's all it is. So it says like, the data you're looking for under this label is gonna be here. And you know the label, you don't know the number, but you know the label. So you'll be able to put these two together. And that's where the linker comes in. The linker takes our object files that we've compiled before, and then it produces either a dynamic library or an executable. We call those images. It takes all of the object files and includes them, all the symbols that were in the object files, it includes them inside that image. Then if we provide any static libraries, it takes those static libraries and includes all of their symbols inside of it. And then if we provided and used any dynamic libraries, those are included as so-called load commands. And load commands are essentially for the dynamic loader that runs your application to say, we need this framework or library, please find it and load it into memory. I have a question here. When you see this, we have the dependencies, a.framework, b.framework, and then we have our foo.o, and we say we link it. What do we get? Anyone? No, not executable. The answer is we don't know, because I didn't give you all of the information that you need to know. Sometimes you don't even know yourself what the information is because you need to look. And that's where the static versus dynamic comes into play. So static libraries are just a bunch of uncompressed object files. And I like to say that it's just a bunch of object files in a trench code because it's like, oh, I have a library. Well, you don't have a library. You have a bunch of files that don't work and you can just use them. And it still needs linking. So it's kind of a misnomer when we say we're statically linking, and it comes from how we build the final executable. Because we say, oh, we're using static linking. And that's because we link our code, basically all of our code, or most of our code, statically into the final executable. And then here we have the dynamic one. So that's a final binary or image. It's close to immutable. We can't really change it much. We can strip some symbols. We can strip some symbols that we don't need, so we can make it smaller. But we cannot change things. We cannot remove parts of that binary after the fact, right? Like we can say, oh, we don't use this part, so we can just get rid of it. Everything that is global and publicly visible will just touch everything, and that will be basically used. And this is what is produced by the linker. And the good thing about dynamic images is they can depend on other dynamic libraries and images. Funnily enough, if you have an executable, you can depend on it from other executables and use its symbols. Even though it's an executable, so you might be like, oh, weird, but it works similar to jar files. Jar file could be executable, but you can still load it as not executable. Why do we use dynamic? Why did the dynamic thing come up at all? How many of you are doing mobile? At the droidcon conference, this is a very relevant question. Some people didn't even raise their hands. So you're at the wrong conference, aren't you? Never mind. So for everyone doing mobile, the first point, caching, means build caching. So when we are building our code, if we have a dynamic library, we can cache it on servers, we can download it, and then just use it. When we're talking about like the caching in the broader sense, for example, on Linux, you can have .so libraries living in the system folders and being shared between different executables. And that way, you don't have to download it every single time, as long as the versioning is right, common problem, and as long as your program basically knows where it would be found. And with that comes reusing memory space. Again, on mobile, we can't use that because our apps run in a sandbox, basically in a container, and we load everything again. But imagine you have a huge dynamic library that's living in the system folders. It's a gigabyte, and everything that you want to use needs to be loaded into memory. So now you have opened two apps, both are using the same library. If they are linked statically, even though they contribute a minimal amount, few kilobytes on top of that library, so they're just providing you access to the library essentially, just different. You now loaded 2 gigabytes to your memory because you need to load all of the symbols twice. But if you have, and if everything's configured correctly, your apps will load into memory, and then that dynamic library gets loaded next to them and reused in both. So you're essentially saving a gigabyte of your memory. With that comes Common API. So if you have a static library, all the symbols are in your binary, and no one else can use the same code unless they linked against your executable, which, while we can do that, nobody does. And so if you have multiple executables that need to communicate together in the same memory space, dynamic library is the way to go because they can reuse it, they can reuse the same memory layouts, and so on. And now the two last points, faster compilation time and slower program startup. It's complicated. So if you are not changing your dynamic library often, and you're just changing whatever is using those dynamic libraries, then your compile time will be faster because you won't need to link against everything. You won't need to include all of the symbols and link them together, especially if those libraries are big. However, if you're doing Kotlin Multiplatform and the main thing you're editing is your Kotlin code and you're building that into a dynamic library, you will be rebuilding it every time you change it. So you lose that faster compilation time because you won't be able to cache the build result. And the slower program startup is basically caused by the dynamic linker having to go through all of your dependencies and linking everything together. So if you do that during build time and you produce a single executable with no dependencies essentially, you've done that work that then doesn't have to be done on the startup. Today, the dynamic loader is very fast, so unless you have a lot of dynamic dependencies, you wouldn't know this, but it's still a consideration, especially on the slower devices. So, can we answer what's the result now? Still kind of no. Let's say the A is dynamic library, B is a static library. We still don't know because we need to decide what we want to build. But let's say we want to link, so link, not static link. And in that case, if we say who's going to be an executable, we end with this. So we have the a.dylib. We need to include that in our bundle, and we need to ship that. And then we have foo, which is our executable, and that contains b. So in the end, oh, that's really washed out. In the end, what we see in the binaries, if we take a look at like the symbols in the binaries, we'll see that A1 and A2, if you do remember, I don't expect you to, way back in one of the slides, we have declared those like A1, A2. It doesn't matter. We have A1, A2 in the dynamic library, and then our foo executable, because B was just the .a, the static library, is actually containing, what the? Sorry about that, some notifications. You should close all your apps when you present. But I was, no, never mind. And so foo is containing that B symbol inside of it, as I mentioned. And then when it comes time to execution, we have the dynamic loader. There's a lot of steps that it does, how it puts things into memory, how it finds everything that we won't go through. It's not that important. The important part is you need to give it all the dynamic images that are required for your app to run. And you get to that by looking at the executable and the load commands the executable has. So our executable has just a load command for A. So we just need to provide A. But if A had dependencies, then it would have its load commands. So let's say A would depend on C, and you need to provide C as well. Now that we've seen the differences between regular JVM and native, let's take a look at Kotlin native and how it comes all together. I like to say that Kotlin native produces native binaries, not that Kotlin native is native. Because there's a slight distinction in those two that hopefully will be noticeable when we go through it. Now, if you remember dependency management on native, that it was like, yeah, we don't really do that here. And then with Kotlin native, it's like, yes, we do have dependency management, and it's worse because we now have both of those worlds, and we need to make them work together. So everything is complex, and it's difficult to get everything working, and there are cases where things are not possible at this point. But looking at it a little more in depth is we essentially have three things in Kotlin native. We have the C interop, which we can use to give header files from other native libraries, and then it will provide us with interfaces and declarations that we can call from our Kotlin native code. Then we can depend on other Kotlin Multiplatform or Kotlin native libraries, which are .klib, and those we get from Gradle, from Maven Central, or whenever other projects in our modules in our project, and so on. And then we can use CocoaPods. I would tell you shouldn't, but you do you. You can use CocoaPods to actually like say, oh, I have this iOS framework C, please get it for me and get it ready for me. So the compilation for Kotlin native is now similar to the JVM one. on the left, you can see the C interrupt working. It takes the h file, so a.h, and then produces a.cinterrupt.klib. So it just produces a klib with all the metadata that we need to have. And then we have bklib, which is a regular Kotlin multiplatform dependency. All of these klibs have Kotlin IR. And that's an intermediate representation of your code. And it's not something you can just run. You still need to produce something from IR. If we went to compile this into JVM target, it would take those IR files and produce Java bytecode from them. But in our case, right here, we have the Kotlin foo.kt, which is our Kotlin multi-platform code. We depend on those IRs, and then we produce another IR and bundle it into a klib. So that was our first compilation. And how many of you use KMP? Okay, and then keep your hands up if you know there's 2 compilations. Okay. You're excused from not knowing that there's a second compilation because it's not easily visible. When you run Gradle and you want to build your framework, you start building it, and you look at the tasks, the first one will be compile Kotlin for iOS ARM64, for example. And the second one is gonna be called link for iOS ARM64. But actually, the link is compile and link. And it's because our IR is not machine code, and we need to get into it. So we take all of the klibs, we extract them, and then we run the second compilation that will actually produce the native code, the machine code, Kotlin foo.o. Now, the second part of the link task, the link Gradle task, is the linking, where we take over the klibs and produce our libraries, our native libraries. If we have everything set up to produce a static library, it works. We get Kotlin foo.a, and we can give that to Xcode, we can ship it, we can do whatever we want with it. But if we want to actually produce a dynamic library or an executable, it won't work, it won't compile. And the reason for that is we are missing A as a dynamic library, because that's our dependency that we need to include. We just gave cinterrupt the header files, so it needs those symbols, and it needs to get them from somewhere. So we need to ship a.dylib and Kotlin foo. And with that, let's take a look at common problems that look at that dependency problem. We'll start with depending on static library. If you remember, I mentioned that dynamic libraries can depend on other dynamic libraries. It's not so for dynamic libraries depending on static libraries, because dynamic libraries include static libraries. And so what happens if we have 2 dynamic images here? We have our Kotlin foo and main, which can be Swift, Objective-C, anything, Rust even. And both of them need things in A. So when you're compiling them, you're just using a.h, right? Your header files, your interface. But then when you need to link them, what do we do? So we just do what you saw here. If we just link it this way, we get this. We get Kotlin foo that has a1, a2, a Kotlin foo, and then we have the main, which has a1, a2, and main. And now this may work. You may be able to run this, and you could be like, yeah, it works. I may see some warnings in the console when it's running, depending on whether you're using Objective-C or just regular C. And then at some point, something changes, maybe the order of the compilation or order of the loading, and you get weird behavior, or it straight up stops working. And that's because those symbols are now duplicate in your program, because both of these dynamic libraries or dynamic images get loaded into memory, linked together, but they both contain the A1 symbols, and they don't have to be the same A1 symbols, just the name is the same. So make sure you don't do this, make sure you don't have duplicate symbols. But how do we actually resolve this? Now, the first problem oh, I forgot to tell you when this actually happens, because you'll be like, yeah, just don't do it, duh. But it's more complicated than that, because when you're integrating with Swift Package Manager, Swift Package Manager likes to build everything as a static library, and then link everything into your final executable. But when you use CocoaPods, or in different way you use Kotlin native, and you want to build your Kotlin native as a dynamic library, you usually depend on other dynamic libraries. You don't put everything in. And so your A dependency gets compiled for Kotlin into a dynamic library, and you depend on it, and you link against it. And then the main links against your foo, but it depends and links into itself A. So what it looks like is this. You have Kotlin foo, it depends on A1 and A2, and then we have main that has A1, A2, main. And this will blow up, because when you try to, hopefully when you try to compile it, but depending on what you do, and if you try some workarounds that I'm not gonna tell you, they exist, but I'm not gonna tell you how to do them, because you shouldn't be doing them, you can actually get it to compile and link and deploy, and in debug and release it will work. So where's the catch? It won't work if you use Xcode 16 and up, and you deploy to App Store. Because if you tell the linker to just ignore it, it's gonna be fine, it doesn't get encoded into the links, and then when it's stripping all the symbols that you don't need, so your binary is as small as possible, it's gonna be like, oh, we don't need those, get rid of them. And this step only happens when you're uploading to the App Store. So only hopefully, when they open it for review, it will crash for them. If they don't open it for review and just deploy it, which I hope is not happening, it would crash for your users, and then you need to publish a new version. So, solutions. This first one, if you do it, I can tell you right now, being an iOS developer myself, your iOS team won't like you. And that's because of how everything looks together. So what we're doing here is we take A, and we link it as a static library directly into the Kotlin one. So now our Kotlin library looks like this. So we have Kotlin foo, we have A1 and A2, and everything is in our public interface. So when they write their Swift code in main, they would only do import Kotlin foo, and they would use A1 and A2, and your Kotlin code, obviously. But then imagine if A1 is all of the Firebase declarations, and then A2 might be some payment processor. So instead of them importing just Firebase, because they want to use Firebase, they now have to import Kotlin foo and get everything. And as your Kotlin multiplatform gets bigger, you would be importing more and more. And then you basically take care of their dependency management, which is nice, but you pollute their namespace a lot. The second option, and the one that I would recommend, is switching your KMP compilation to static. So instead of producing a dynamic Kotlin framework, you produce a static framework, which, again, is just a bunch of object files. And therefore, you don't need to say what you're gonna link against. You don't need to include that final piece of dynamic library. And Kotlin foo, as we saw, will not include those symbols. So then main can depend on and link into itself A, and it will depend on and link Kotlin foo, and everything will be nice and well, and everything will live in the final executable. Another common problem is depending on a system library from your Kotlin multiplatform code when the Swift doesn't depend on it. And this is usually SQLite 3. So you go on, you include it in your Kotlin foo, and this only happens, and this is why a lot of people don't use static Kotlin libraries, and they use dynamic, because with dynamic this doesn't happen, because the load command is included for SQLite. But if you change it, based on the previous slide, to static, you may get, oh, undeclared symbol SQLite. And this is something your iOS people will get, not you. You will be like, I'm fine. I just produced you a nice static library. Do what you will. Solution one, tell them to fix it. Just add that link, add it into your, like, you don't use it, but you do now. A better solution, auto-linking. You can actually tell Kotlin, you can include this linker option when you're compiling the object files, and then those include the information that when you're linking me, please include this. And then they don't need to do that. So this is really helpful for your iOS team. They will appreciate it. Because this is what happens automatically for them. And the last problem is ignoring warnings. Who here has a bunch of warnings in whenever they build? Don't be shy. I know all of you. Now, I know that a lot of people like to even switch warnings as errors, which is really helpful. And I do recommend that. I wish I had the discipline to do it myself. However, in native, it can really bite us in the behind. Because essentially, warnings are errors in native. It just usually results in undefined behavior. So if you have duplicate symbols, they are included in multiple places, as I mentioned, and it's really undefined which one is used. You're basically playing a lottery every single time. And most of the times you will win, which is weird. But then there will be times, and it's usually gonna be users or your CEOs that will find those lottery numbers that didn't win, and they will be mad at you. So heed all the warnings during the app startup. So what I want you to take from all of this. Static linking is your friend. You may see a lot of tutorials saying that you should just use dynamic linking. It's sometimes faster, yes, but the static linking has a lot of benefits that are not visible right away. And if your team switched, iOS team switched to using Swift Package Manager, they will thank you for this. Make sure to learn the native build process. Kotlin Multiplatform and now IntelliJ IDEA with the Kotlin Multiplatform plugin can do a lot of heavy lifting for you, but you should still learn it, even though it works. But do you know why it works? I recommend finding it out before you need to release your app and everything breaks. Heed the warnings and have fun. And expect weird issues, it's native after all. Now, we don't have time for questions. So if you have any, just look for my signature flannel and just go and ask questions, and I will answer it. Now, all of those people, and because all of those people were me, recommend Sky. So if you use KMP, make sure you use Sky. It will make your iOS developers incredibly happy with how your API will look like. And lastly, get in touch. I'm terminally online. I will probably follow you back if you follow me. And I'm on both Mastodon and Blue Sky. Thank you very much for your attention.